Hey, welcome back to another episode of Tensorflow for NLP. In the last couple of videos, we got our data ready to build a model for sentiment analysis, and in this video, we're going to do that. So we're going to cover a little bit of a high-level explanation of what an RNN is and how we're going to use it to complete our task. A lot of people are afraid of recurrent neural networks, and they're afraid because they've looked at them when doing something like image recognition, where it doesn't really make any sense. It's really hard to understand because it doesn't seem like it really fits for the problem. Well, with text, it does make sense, and it is intuitive to understand. Recurrent neural networks take into consideration past dependencies to make a decision about a whole sequence. So in this case, we have a sentence, I like dogs, and we're going to try to figure out what is this sentence about by looking at the whole sentence. If this word here was hate, it would have a completely different meaning at the end. So I'm going to show you how this works. We feed this data in to the network as a sequence. What's really cool about what's happening here is that each one of these units here is connected to each other. So when we pass like into the network, it's also getting information from the previous time step. These are the outputs of the network, and this arrow here indicates the hidden state of the network. What we really are concerned with is this final state here, where it's the final output. So we've fed all the information in, and then this would be the final output. We don't care much about this, or either of these. We only really care about the final output. So you might be wondering how we're going to pass our data into the LSTM. In the last few videos, we were doing stuff with just taking the word pairs, but now what we're going to be doing is we're going to be passing the full sequence, the full sentence into the network. So what we already did was we took the sentence and we were able to turn it into a list of tokens, and in the very last video we did padding the sequences. So this sequence is going to be max sequence length, right? And then after that, what we're going to be able to do is take that entire sequence and do an embedding lookup function on it. So now we'll have the entire sentence, including the padded zeros, translated into the embeddings or the vectors found within the word vector matrix or the embedding matrix. Then we can take that sequence of word embeddings and pass that into our LSTM. From a high level, what we're going to try to do is take this lookup here, which is our list of word vectors. We're going to pass it into the LSTM, and this LSTM is going to produce outputs at every time step, so t, t+1, t+n. So that'll be stored in the LSTM outputs from TensorFlow. Then we're going to have to extract the last output, because that's the only output we care about. So it's this one, and we'll call that last. And we're going to make a prediction, which will be last times weight, add a bias, and the end shape of this prediction is going to be number of classes, which in our case is 2, because we're only trying to predict positive versus negative. We'll compare our prediction to our labels, and then we'll be able to calculate a loss and then train our model. Now we're back inside of our Word2Vec file, and we're going to try to implement what we just talked about in code. So first, we're going to delete everything after this data and labels that we created. So just go ahead and just chop everything off. I'm going to give myself a little space. All right, so we're going to create a new function. We're going to call it model. And we're going to have to instantiate our new placeholders, our variables, and everything we need to make this LSTM. So the first is going to be the sentences or batch size list of sentences of sequences. We'll call this x. And it's a placeholder, and it's going to be int 32. And the shape is going to be none by sequence length. This allows for a variable batch size. And we're going to call the name x. Labels. We're going to call this one hot labels. Call it y equals, and I'm going to copy this. going to change the name to y, and this is now going to be none by num classes, because it's a one-hop vector of just our two classes. So now we're actually going to cast our y to be a float, because later when we do some math, it's going to get messed up if it stays as an int. So cast our label as r2 float 32. tf.cast does this, so we'll say y, and then we'll pass it what we're trying to convert it to, so tf.float 32. And now we're going to create our embedding matrix. So instantiate our embedding matrix. I'm going to call it embedding, and that's going to be tf.variable, tf.random uniform, and then it's going to be our shape is going to be vocab size. This is the same as last time, guys. So by embedding size. And we want those to be from -1.0 to 1.0. And we're going to call it name equals word embedding. Perfect. Okay, now we're going to look up embeddings. I'm going to call this embed lookup. That's going to be tf.nn.embedding lookup. Everything's the same so far, pretty much. The only difference is that now these are sequences instead of just single integers. Now we have a sequence of integers. Okay. Now what we're going to do is we're going to instantiate an LSTM cell. That's how you have to do this in TensorFlow. You have to create a cell first, and then you can go from there. So the cell is that state that we're passing stuff into. So we'll say create LSTM cell, and it's going to be LSTM cell equals tf.contrib.rnn.basic LSTM cell. And we're going to pass that the number of hidden units we would like to be inside of that cell, which we already instantiated, I think. Yep, we're going to use LSTM hidden units. And now what we're going to have to do is we're going to create the initial state for our LSTM, which is going to be instantiated at zeros, and it'll learn as it's given more information. So at the very beginning, at state 0, it's going to be all zeros, and then as we pass it information, it's going to add value to that. So in order to do this, we need to get the current batch size, which we did not specify because it's none. So in order to get this number out of this variable, we're going to go ahead and have to evaluate the shape within the graph. So extract the batch size. This allows for variable batch size. I'm going to say current batch size equals tf.shape of x, and we want the zeroth element of that because that's going to be our batch size. Again, because it's going to be this by this. Okay. And now we can create that initial state. So create LSTM initial state of zeros. And we'll call it initial state, and we'll call that, and we'll do, so we have to use our LSTM cell, and we're going to call 0 state. And we're going to pass out our current batch size, if I can talk. And the D type is going to be tf.float 32. All right. Now what we're going to do is we're going to wrap our LSTM cell in a dropout wrapper. So what this is going to do is it's going to add dropout to our LSTM to avoid some overfitting problems. And And you'll see how this works. So it's LSTM cell. So it's the same LSTM cell. We're reinstantiating it. And what we're basically going to do is we're going to wrap dropout around it. So tf.contrib.rnn.dropout_wrapper. And the cell is one of the parameters that it takes, and we're going to pass that our LSTM cell. And then we have to specify an output keep probability. So this is the amount of dropout. Perfect. Now what we're ready to do is to wrap this cell in a tf.nn.dynamic RNN, which will fully put everything together. So we're going to say value, comma, underscore. And I'm going to explain this in a second, so I'm just going to write this first. I'm going to say tf.nn.dynamic RNN. And this takes a few parameters. The first one is LSTM cell. Next is the embed lookup, because again, we're going to be passing in our looked up embeddings. Our initial state is going to be equal to our initial state. And our dtype is going to be equal to tf.float32. Okay, so remember when we were talking about the outputs of the network? That's what this is right here. That's our value. So our value is going to have all the outputs for the across the entire LSTM. What we really need is the last one. And this here, this underscore, is the hidden cell state. So it's those little arrows we're drawing in between the cells. We don't care about this, so we're just going to call it the underscore and forget about it, basically. All right. So before we grab this last output, we're going to create our variables for our weights and our biases. So weight equals tf.variable. That's a random normal distribution. And the shape of this is going to be LSTM hidden units by num classes. And then we're going to create our biases the same way. tf.variable, tf.constant is what we're going to pass in here, and then 0.1. Our shape of that is just going to be the number of classes. Perfect. And now we have to do a little bit of transposing and manipulation in order to grab that last value. So the first thing that we're going to have to do is reinstantiate value as a transpose version of it. So we're going to say tf.transpose value 1, 0, 2. And this is just going to manipulate it so that it's a different shape. I believe this is going to turn it from like a none 250, 256 shape to a 250 none 256 shape. So it's a little bit confusing, but what you need to know is this is getting it in the correct format for being able to do the multiplication at the end with the weights and the biases. So now that we've transposed that, we need to get the last output. And you can't do negative indexing in TensorFlow for some reason, so you have to do something called gather. So I'm going to say tf.gather the value that we have. I'm going to say the int of the value.get shape 0 minus 1 because we want to get that last value. So this will basically get the shape of value, and then this -1 will basically be the last index, right? Because it's 0 index, so the last one is going to be the length minus 1. Extract last output. Okay. And then finally, we'll be able to make a prediction. So our prediction will equal tf.matmul our last value by our weight. We're going to add the bias. Perfect. And now what we're going to do is, I'm going to skip straight to loss. So calculate the loss given prediction and labels, and that's going to be loss equals tf.reduce mean tf.nn.softmax cross entropy with logits v2. I'm using v2. It's the new one, I guess. And I'm not really sure why I used it, but we're going with it. Logits equals prediction, because those are our logits, and then labels are going to be our y's that we passed in and then casted. So these are our labels of yes, it is positive, or yes, it is negative. And we're going to compare those. Oh, I'm missing something, I think. Yep. And then we're going to declare our optimizer. In this case, RMS prop. And we're going to say optimizer equals tf.train.rms prop optimizer. And we're going to say our learning rate equals our learning rate, which I believe we have up here. Yes. And then we have to say dot minimize. What do we want to minimize? Our loss. And we're all set. So now we can return our optimizer, our loss, our x, our y, and our prediction. Awesome. So that's our full model. Finally, our model is built, our data is ready, and now in the next video we'll be able to talk about training this and being able to get some results with our sentiment analysis model on these reviews. I hope this helped, and if I can answer any questions, please go ahead and ask in the comments. I'm happy to help, and I'll see you next time. Thanks for watching.